today we have with us Dinesh Kartik. He'll be talking about uh, the mathematics behind AIML. Yeah, you can start now.
Yeah. So yeah, present the screen.
You can't?
Yeah, no, I'll present. Yeah.
Uh,
So are you able to see this now?
yes, yes,
Uh,
yes. But
yes.
it's black. Is that what you're
Yeah,
saying?
yeah,
Okay.
yeah. So it's okay. Why it good? Yeah. Uh, so so first of all, like we'll be seeing the definition of what it means to uh, what it means by a machine learns a certain thing. So we'll define what is it. So the framework that we are going to follow is the statistical learning framework, and everything that I'm going to follow is from the book by so understanding machine learning by Shy and Shy. So this is like a standard book in machine learning theory. So so what it uh, so we'll define what we mean by machine learning initially. So we'll start with an example. So suppose you are stuck in a Pacific, Pacific island. So you are stuck in an island, and you only have the access to eat papayas in the island, and you want to see you want to learn. So I've not defined what I mean by learning here, but still English terminology learning here. So you want to learn by seeing a papaya whether to eat it or not, kind of thing. So this is an essential skill to survive in this island now. So so basically, so let us so the edible. So a papaya being edible depends on a lot of factors, but so let us consider it only depends on the size and the color. So so here color, I mean by the ratio that it is yellow east to green. So if it's more yellow or the other way, or yeah, so if it's more yellow, then it's like the high, it will be high here. So it's like the more yellow it is, the more edible it seems to be, or like the more ripe the papaya is. And like if the size of the papaya is small, then it's probably not much edible. So so you have a certain sample here, and you want to predict on a new papaya by seeing it whether it's edible or not. So am I clear till now?
Yes, yes.
So so you may not try infinitely long. So you for the initial days you might eat. So I'll define what are y's and y and x's. So you might try out eating first n papayas, and so this is so everything is like normalized kind of scenario where this is 101, everything is like in this square, and this is this this belongs to, this is a tuple, and this is 0 or 1, whether is 0 is like not, you can't eat it, and 1 is you can eat it. So basically you have 3 here. It's like the color, size, and whether you were able to eat it or not. So first you have tried n papayas, and with the experience of these n papayas, you want to predict on the n plus 1 papaya that you're going to eat by seeing these two characteristics. You want to say whether the next papaya is edible or not. That is the main problem in supervised learning. Am I okay till now?
Yes. Hmm.
Uh, so we'll define our framework here now. So we now have the domain set. Domain set is similar to the ordered pair exercise here. So we have the domain set where the characteristics comes from, and you also have the label set where you want to classify things. For simplicity, we just assume for now this to be 0 or 1 or -1 or 1. So for now, it's just binary classification. And so this is domain set. This is label set. And then you have training set. So this belongs to X cross Y. So this is called training set. So this is the data that you initially have. So what is our objective? Our objective is to learn a function from X to Y that performs good in a certain sense on unseen data. Am I okay till now? So we also have f of xi to be yi. So this we have till now. So we want it to be good in certain sense. So we'll define what it means to be good. So let us assume, so if we have the distribution of x, then it's easy to determine. So if you have the distribution of the papayas at any time, I think you can definitely say whether to eat a papaya or not. So the underlying distribution of the set x is still unknown. So we would like to measure the success of our h that we find from a machine learning algorithm. So let D be underlying distribution. So let f from x to y. So let f be the actual function that you are going to find. This is our aim. So this is our aim, and this is what the algorithm gives you. Okay. So we are going to define laws with respect to the distribution and the function that we want to find to be probability that x belongs to D, h of x is not equal to f of x. So am I okay till now? Is this okay? So this is how we define the laws.
Okay.
Okay. So this the same as x such that So there are many.
What do you mean here?
There are
X
many things
belongs to
unknown
D.
here. Huh?
D is a distribution, right?
Yeah.
And X is a parameter. So what do you mean by X belongs to D?
X belongs to X.
So X is
In
sample
the
from D,
above.
right?
X is the distribution. D is the distribution over X.
Okay, no, the above where you wrote the probability part, like X and some notation, then D. Like, what does this notation mean?
Okay. So like X is sampled from X kind of thing.
X is sampled from D distribution. You are saying that? Okay.
Yeah.
Okay.
So belongs to X. So you want to measure how wrong your function that machine learning algorithm gives with respect to the actual function, assuming a distribution. So there are like two things that we don't know till now. We don't know that the function f and the distribution d. So these things we don't know till now. So this is where the statistics part enters. So we do everything empirically. So okay. So we want our heads to do good on the unseen data, but if it also want to do on good on the unseen data, we also want it to do good on the sample. So we want heads to do good on the sample. So we want heads to do good on the sample. So with respect to a sample, we define loss. We define this to be the order index I such that so this is how we define loss on the sample. So this is just the number of the size of the indices where the function does not agree in the sample. So this is how we define error or the risk. Risk is also error is the terminology. So we want this also to be less. So the question that we here ponder is whether minimizing the error on the empirical risk, this is called whether minimizing the risk here also minimizes the risk LD, F, this risk, the population risk. This is what the analysis is all about. So one strategy to find our hedge is to find. So we'll go later where we'll show this empirical risk is close enough to actual risk. We'll shift the discussion, that part of the discussion, to the later part.
What do you mean by actual risk? What do you mean by actual risk?
So actual risk is the risk defined like this, where the D is not found and F is also not known at all.
Okay.
So this is what how we define risk, and this is what we define risk over the sample, and we want to see whether this risk is close enough to this.
Close enough as in?
So the function that minimizes this empirical risk should also minimize the population risk is what we want, right?
Okay.
So because we don't know the function f and d, the distribution d, we can't So we can't directly minimize the population risk. So instead, we try to minimize the empirical risk, and we want the function that minimizes this also want to minimize the population,
Okay.
right? So, so the paradigm or the scheme of the algorithms that all the machine learning algorithms follow is called empirical risk minimization, which says is the function that minimizes the empirical risk also performs better is what we have the machine learning theory people have proved. So what they try to do is they try to minimize the empirical risk. Uh, so there is one uh, what do you say caveat in this. So can you point out something here? Can you suggest a function that always does good on the empirical and performs very badly on the population? Hmm? So, so you can.
So, like
So
on empirical, you by good you mean it says everything almost perfectly.
yeah. So that is like good in the sense like LS of H is zero and this is non-zero. So something like if you take H of X to be one or okay to be yi if xi comma yi belongs to sample, or you otherwise say something zero otherwise. So this function always does very good on the sample, but it may not generalize too well.
Uh-huh.
Right?
Hmm.
So it's like in the island, the first 10 papayas that you encounter will be like not even edible, and like you predict every other papaya that you're going to see in the future as like not edible. So this is how bad you can do. But what we are going to prove is the probability that you're going to encounter all the bad papayas in the first 10 samples would be very less. Uh, are you clear with this now?
Um, so, like what you're saying is
So,
like we we remember all the points is what you are saying.
no, it's like the probability that this type of sample,
Huh.
the sample in which everything is bad,
Huh.
occurs is like very small.
Huh.
I'll clear this. Uh, hmm. So yeah, so you understood the problem here, right? So this performs very. So I can cook up some distribution where the sample is such that it does perform very good on the function H performs very good on the sample, but will be worse on the other unseen data. Is it okay till now?
Yeah. So it
So
basically remembers what it has seen and doesn't know anything about anything else.
yeah,
Ah.
so this is not a good predictor that you want, right?
Ah. It's not a predictor.
Yeah, it's not even a predictor. Yeah. So these type of things are called overfitting.
Okay.
So it's like it's like you have different types of points here, and you try to find a function that goes through everything.
Huh. Huh. Huh.
So so this has too much error on the unseen data. So this is where this is where this is where prior knowledge helps. Here, a prior knowledge, in the sense, this can be from the domain. From the domain, in the sense, so in our papaya case, so there can be, so this is where you see, so this is the distribution of the papayas. So you can have, so you can assume that there will be a small rectangle in which all the edible papayas lie in. So you can safely assume this, right?
Why should it be a
So,
rectangle?
what I mean by this is, so the size of the papaya lies between, say, like 7 centimeters to 10 centimeters, and color lies between this numbers.
But like
No, okay, right?
oval kind of thing. Okay, okay.
Huh?
I thought it could be like oval kind of thing.
Yeah, it can be. Yeah, it can be like this also. Yeah,
Huh.
yeah, it can be like this. But so what I want to say is, like, you can't exactly find the exact distribution or the shape that I'm drawing here. So you try to do justice with respect to the rectangle that you want to do. It's like in the case of linear regression, you try to, so you have a data and you try to
Put a line.
justify the data with respect to a straight line, right? In the same sense.
Oh, so here we are like fitting the rectangle to this figure.
Yeah.
Okay.
So this is where the prior knowledge comes from. So we'll define here. So let h. So here the function h is called hypothesis. This is called hypothesis, and this h is called hypothesis class, and this is a subset of all the functions from x to y. So this contains all the functions. So this contains all the functions, and yeah. So for the case of like linear regression, this hypothesis class would be all the straight lines passing through origin kind of thing. Okay, right? So instead of focusing on all the functions, you want to narrow you want to narrow it down to a certain subclass of functions that with respect to the domain knowledge that you have.
Okay.
So,
And how would you do that? Like,
so this basically depends on the problem that you're trying to solve.
okay.
So
Can you give some example?
So the case is like where you want to find a linear predictor for a data that you see. So
Yes.
then the hypothesis class would be set of all functions. So a set of all straight lines.
Yes.
So you want so then this will be like set of all straight lines. Kind of functions. Okay, right?
Okay, but like
It can be.
if I want to find straight line, but it might be the case that original function is not straight line.
Yeah.
But that's what. Okay.
It need not be straight line. Yeah.
Okay. It's what I am predicting that it should be straight line.
Yeah, you are guessing it to be straight line. Yeah.
Okay. Okay.
So you are guessing it to be a straight line. you want the straight line that you guess, the actual straight line that you guess, should be as near to the function, the actual function as possible. Okay, right?
Yes, yes.
So yeah, this is what we want to do. So the thing that we'll do is, so here is the thing. So you define, so this is what empirical risk minimization scheme is. So you select a hypothesis from our hypothesis class that minimizes the empirical risk. You define empirical risk to be this. Okay.
Okay.
So this is the scheme that we want to follow, and you want to justify that the scheme works better. That is what we want to know, right?
Huh.
So, so the term better is also very subjective now. So I'll define what you mean by learning also. Yeah. Yeah. I'll define it here. Yeah. So we'll define, so so pack is probably yeah, approximately correct. So this is like probably approximately correct learnability framework. So you want to define learnability in terms of with respect to a hypothesis class. So so let's say the hypothesis class. So let H be the hypothesis class. You want to say whether this hypothesis class is learnable. By this, what I mean is you define any distribution on a set, and you define any function that you want to learn. Then whether can I design a learning algorithm on H that does better in a certain sense. I'll define what it is. So we'll see this here. Yeah. Yeah. So a hypothesis class H is pack learnable if there exists a function m subscript h from 0 comma 1 into 0 comma 1 to n, and a learning algorithm with the following property, that for every epsilon and delta there, and for every distribution x, so I'll yeah, so reading this will be confusing, so I'll write it here. Yeah. So if you have a distribution d, so d be a distribution over x, and y be 0 comma 1, and h be the hypothesis class, you say this hypothesis class performs better or is learnable, or you can give a predictor function from this h that performs better in a certain scenario, as so you want, so let this be the function that you want to learn, let f be the function that you want to learn. Then for every epsilon and delta greater than 0, there exists m such that m naught. For all m greater than or equal to m naught, if the sample size is greater than or equal to, yeah, yeah, then so let A be the algorithm. So A takes the input S and gives out the function H. Then you can say that so I'll explain it verbally. So what you're basically saying here is, so for every epsilon and delta, you have a you have a number m, which is the minimum number of sample size that you require, over which there exists a learning algorithm that will give you a hit whose error, whose empirical error is less than epsilon. Uh, okay till now?
This is definition of what learning a function.
Yeah, what it means to be learning.
Okay.
So I'll write it properly. Yeah. So in here, like when, so you have this hypothesis class coming from the domain knowledge, right? You want to quantify how good is your hypothesis class. Okay.
Yes.
So you want how good your set of all possible predictors can be. So that is how. Okay. And so I'll reformulate the definition. So H is fact learnable if there exists a function m that depends on the hypothesis class this is okay. This is for the epsilon and this is for the delta to natural number such that there exists a learning algorithm A from this is for the sample. So this denotes the sample. So the learning algorithms take sample as the input and gives out a function. Okay, we'll denote this as it. So it gives out a function h by taking in the sample that for every distribution D and whatever function that you want to learn from the hypothesis class, and for every epsilon and delta greater than 0, so this is where we'll define probability that yeah, the function that learning algorithm gives as output, the the probability that the loss is greater than epsilon is less than delta. The probability of this happening is less than delta. Okay.
So like the function, the actual function should belong in your hypothesis. So
Yeah.
you know
So,
what the function should
so
look
this,
like.
yeah. So this is a strong assumption to make.
Huh.
Uh, so there is one more definition of learnability, which is called agnostic back learnability,
Huh.
where we relax this assumption of there exists a
Inclusivity.
function from the hypothesis class, and
Okay.
you define the same thing.
Ah,
Yeah.
okay.
So the aim was to prove a small result that if our hypothesis class is like finite, then it is flat learnable. So the learning algorithm here would be the ERM algorithm. And the function that ERM algorithm returns performs good in this sense.
Which
That the
algorithm?
loss, huh?
Which algorithm?
the so the algorithm scheme that we want, the ERM algorithm.
ERM.
So this is not a particular algorithm, like this is the scheme in which you design the algorithms to be.
Okay.
So the scheme is like you try to, so you have H belongs to the hypothesis class. You find H that minimizes empirical error. Empirical error would be this thing. So you find H in our hypothesis class that minimizes the empirical risk.
But if f belongs to your hypothesis class and your hypothesis class is finite, then you can
Yeah,
just go over all the functions and check which of them fit the best.
yeah. But you also need to guarantee that the error won't be greater than epsilon, right?
Uh,
That it any epsilon. So
so
you want a sample size
uh,
to guarantee
we
to
know the
guarantee that.
sample.
Uh, uh,
Uh, like what we are guaranteeing here is only over the sample, right? So on sample, it should behave the best, and the function should belong from H. So I'll go
yeah,
over all the function in H, and I'll find
yeah,
the one for which this is zero.
yeah.
So
What? So yeah. So what I'm saying is, so this is how you define learnability is. So you define. So this is what it means to be learning a function is.
huh,
So if you have a hitch that performs better in the scenario is if you are given a large enough sample, the error is small enough.
huh,
So here our threshold is if the error is less than epsilon, then it's a good function. Okay.
okay,
So if the population error is less than epsilon, let's say it's good. And what we are saying is the probability that the algorithm gives you a bad function is very less. Okay.
so like here while
Uh,
constructing A, do we have any information about D?
no.
Okay.
So if we know, so the only information that we get from D is S itself.
Okay.
Yeah. So the only paradigm or the scheme of algorithms that we have now is like ERM. The least square is also the same like where the hypothesis class is like all the linear classifiers, the straight lines
Hmm.
passing through origin or shifted ones, and you try to minimize so the loss function there would be the square
Uh-huh.
loss of the difference between yi minus the actual thing.
Uh-huh.
And yeah, So you minimize that and say the minimizing over the sample also is the best thing. So, and there is also algorithms called like k-means clustering or support vector machine, those kind of algorithms that also rely on ERM. So, so the what we are so what they proved is the class of all straight lines passing through origin is pack learnable. So if you design any learning algorithm or if you follow empirical risk minimization on a pack learnable hypothesis class, you will be able to learn a function that performs better in this sense. Okay.
Oh, okay.
Yeah. So this is what. So the proof for set of all linear classifiers is pack learnable is long, but I wanted to prove that finite hypothesis class are pack learnable and like try to extend it. But I think like that could be also a little long. Yeah. So this is how you try to make machine learning rigorous. So what I tried to do in summer was which is called risk sensitive learning,
Uh,
where you want to learn a function that minimizes risk in a certain scenario. You want to learn a function that takes into account the risk also.
the the
And you
actual risk, you mean?
no, not okay. Okay. The risk here is different. Okay. Okay. This terminology now is like this is error and risk is the financial risk or risk associated with respect to the
Effect.
uh, yeah, like how how big the loss that that you're going to make with respect to the function that you're going to predict.
Does there exist a function which will give zero loss?
No, you so this is all like probabilistic. So you can say like the loss is less than this with the probability. You can be this certain that the probability the loss won't be greater than this kind of things.
Okay.
Yeah. So so in the sense like if you invest like 1 lakh amount of money, so so what is a right question that you would like to ask? Huh? So like what is the risk associated with it? But here what is risk again? So one way to see what is risk is so with a probability with 0.99, I can say if I invest 10 lakhs, the loss won't be greater than 1 lakh. So is it a good confidence that I can give?
Uh,
Huh?
that is not a good confidence, right?
No, no, no. No, what I'm saying is, so, so, yeah. So if you invest 10 lakhs, what I'm saying is with this probability, I'm saying is you won't lose more than 1 lakh.
Okay,
Okay.
depends on the probability, right?
Yeah, yeah, yeah. So with 0.99 probability, I'm saying you won't lose more than 1 lakh. This is a good term of probability, right?
Zero point
So this
nine nine out of 100 or out of one.
0.99 out of 1.
0.999.
Yeah, yeah.
0.99.
Yeah, however greater you want to be. Yeah.
No, is that out of 100 or out of one?
Out of 1,
Probability
0.9.
वन ही होता है ना probability.
अच्छा वैसा कोई
Yeah,
हाँ.
इशू हाँ ठीक अच्छा ओके
yeah, or
then
else like
then it's a good thing
99% of the time. Huh?
then it's a good thing.
Yeah, yeah, yeah. So, so this is a good measure of risk, right?
Huh.
Hmm.
So what I try to do is like, okay, this is a good kind of measure, but like people in math finance also do is like, what happens in the worst case scenario? Worst case scenario is like, okay, with 0.99 probability, you are saying loss won't uh, cross 1 lakh. But what happens in the scenario where the probability is 0.01? There, the loss might be like 1 crore. Like
Huh.
you don't want that to happen, right?
No, no.
So, so you try to design a function that also minimizes loss in the worst case scenario also.
Huh, 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 huh,
So what I try to do is like we try to show that if we follow this scheme, that minimizing functions over the tail also, like loss on the tail also performs better in the pack learning scenario.
huh. On the tail as in?
On the tail in the sense like 0.01 probability case. On the worst case also, you if you try to minimize, if you try to find a function that minimizes the loss on the tail.
Okay. So here by tail you mean this 0.01 probability.
Yeah, yeah, yeah. So
Okay.
what happens if the 0.01 probability, like the loss can be like too much, right?
Huh.
You try you try to find a function that also minimizes the loss over the extreme case.
Huh, huh,
I'm saying is this also does uh, better in the scenario that I told before, like the pack learning scenario.
huh. Oh.
Yeah, this is what I try to
I
do.
forgot the full form of PAC. What is PA full form? PAC.
Probably
Probably
approximately.
approximately correct.
Probably approximately correct.
Yeah,
Good term, like
yeah,
probably
like
and approximately. Like
yeah, like okay. 1 second. Uh,
There is this
मेरे हिसाब से सही
epsilon
है,
and
तुम्हारे
delta
हिसाब से
also
देख
there.
लो,
That
गलत
is
हो
like
सकता है.
probably and approximately.
है प्रणीत? मेरे हिसाब से सही है, तुम्हारे हिसाब से देख लो, गलत भी हो सकता है. Probably approximately correct.
It's like दो चीज है ना वहाँ पे एप्सिलॉन और डेल्टा तो उसके
epsilon
लिए.
and delta.
हाँ.
So this is like how how accurate you want to be and
That
how
is like
certain you want to be with the accuracy is what. Yeah,
epsilon is like approximation, delta is like
yeah.
probably.
Probably
हाँ.
with, yeah, this approximate you will be with this probability. Yeah. So this is the framework that you have in machine learning. So yeah, this is what people do. Yeah.
So like what people are doing right now, like they don't refer to these theories,
Sorry.
like what these AI people are doing right now, for example in OpenAI or something like that. They don't
No, no, no.
refer to these theories, or not.
So so what happens is like, so they so you now have like neural networks kind of thing,
हाँ हाँ हाँ.
which which approximates every possible function out there. Like it can approximate it. Yeah.
Oh.
So if you have a sample and the underlying function that you want to find,
हाँ.
so by burning certain like, so how large a neural network can be, you can approximate the function that you want to get.
So like for any
So
function, be it
yeah, any
differentiable or
function, yeah,
non-differentiable, it can be approximated like in a mathematical sense to this neural network.
yeah, by neural networks, yeah. So so people don't know how neural networks works, and like people say like it's a engineering jugaad. Yeah.
But it doesn't need to be differentiable also. I mean, not even continuous.
No,
Continuous
it
से
can
काम
be.
चल जाता है इन लोगों का.
Yeah.
No, no, if the actual function is not continuous, can your this neural network approximate it?
Yeah, it can. Yeah, it like. it can be like very, how do I say, very sparse also, like
Okay.
can be continuous at many, discontinuous at many places also. Then also it can approximate. Yeah. It's like the restriction on the hypothesis class is like very weakened now. It can approximate like very large class of hypothesis classes. So
Uh,
one thing that theory people do now is like they want to know how these neural networks actually work.
I mean, they have already proven it, right? Like, if you're saying that it can approximate it within any range of
No,
approximability,
yeah.
then it's done already.
So like this is what people observe. Like
Oh, observe.
they don't know how neural networks actually work. Yeah,
Oh,
yeah. It's like still an open problem, and yeah, like very very active, and like many people say like yeah, it's as difficult as like any other like any other, yeah, very difficult math problems.
oh,
Yeah. So yeah, that is what like ML theory people do.
oh.
Yeah.